Hi, welcome to our session on topological band structure theory. So today we are going to do a Jupyter notebook focused on exercises about topological band structure theory. And among others, we are going to look at the quantum anomalous Hall effect, also called Chern insulators. We are going to check also quantum spin Hall insulators and see what is the robustness of the edge states and what is the relationship between edge states and the topological invariant. So let us start with the first exercise, which focuses on seeing how topological states appear in a system just due to the presence of a magnetic field. So what we are going to do is we are going to take a certain geometry of a certain width, in this case 20, and we are going to create a triangular ribbon and define a certain set of magnetic fields, and we are going to compute the electronic structure of this ribbon at the different magnetic fields and see how the bands evolve with the magnetic field. So here you have how to add the magnetic field. Here we are computing the band structures, and then afterwards we see the band structure. So let us just execute this small example. And so what you actually see is that there will be three different electronic structures. We are going to have an electronic structure for zero magnetic field, another one for large magnetic field, and another one for even larger magnetic field. And the plot on the left is effectively the geometry of the system. So you have a one-dimensional ribbon. The top part is red, the bottom part is blue, and these colors will allow us to know in which part of the ribbon each state is. And this is what we see here on the right. So in this first plot, you see case with magnetic field equal to 0, and so all the states are effectively delocalized all over the ribbon. Then once you add a magnetic field, you start seeing that some states localized on the top and other ones localized on the bottom. And then for even bigger magnetic fields, you see that the localization is even stronger. And something that is very interesting to see is that the states that are localized on the top, which are the red ones, they all have a speed of propagation that is negative, right? So you see that the slope of the energy versus momentum is negative for all of them. And for the blue ones, it is the other way around. And this is very important because this, what actually tells you is that the states are chiral, meaning that on one edge you have states that propagate in one direction, and on the other edge you have states that propagate in the opposite direction. And if you increase the magnetic field, the effect is even stronger. Okay, so now let us go to the question. So in plot on the right, what are the blue, red, and gray states? So red, blue, and gray is effectively the location of the state. And so gray means that the state is delocalized all over the place, or that it is on the bulk, red on the top, blue in the bottom. In which direction do blue states propagate at negative energies? Well, this refers effectively to these states over here, and they propagate towards the right because the derivative of the energy with respect to the momentum is positive. And for the red states, they propagate towards the left because the derivative is negative. Okay, let us move on to the next exercise, which is the quantum Hall effect now in graphene. So before we were taking a triangular lattice, now we are going to take graphene. And so for that, we are going to take a honeycomb lattice, particular with an armchair termination. We add the magnetic field, we plot the geometry, and we plot the bands, and then we get these plots that we see over here. So the overall shape of the bands looks fairly similar, but of course, it is very different in the sense that now here we have electron hole symmetry, before we didn't. And the common thing is that, as you see here, we have states that are localized in the bulk of the ribbon, states that propagate towards the right, states that propagate towards the left, and we go to negative energies, then the role of these states switches. So let us go to the exercise. So now first remove the magnetic field and see if there are states localized at the edge. So we are going to first, let's say, recompute this with a finite magnetic field so that you see that we effectively get the bands that we were discussing before, and then we are going to remove the magnetic field. Okay, so this is with magnetic field, which is the result that we had before, and now we are going to remove the magnetic field. And so when we remove the magnetic field, what you are going to see is that all the states are actually delocalized all over the ribbon. So we no longer have states localized in the positive part or in the negative part, but they are everywhere. And so this is the band structure in the absence of a magnetic field. And you see that you effectively get this Dirac cone that it has a small splitting due to the finite width of the system. Okay, now the next question is to replace the honeycomb ribbon by a zigzag ribbon uh, and see how the spectral looks like. So we now take a zigzag ribbon. And so what we have to do is just to do the same thing, but now with zigzag, right? So honeycomb, zigzag ribbon, and see how the band structure looks like. And so what we are going to see here is that actually now we are going to have edge states. And this effectively comes from the fact that zigzag and armature, they have different edge states. In particular, zigzag has topological edge states. So you see that here there are some bands that are very, very flat. So these bands correspond to states that are localized here on the top edge and on the bottom edge. Then let's move on to the next question. So make the room wider and see what changes do you see in the band structure. So for that, we are going to take the armature ribbon, and what we are going to do is we are going to just do this calculation for two different widths, one with 10, all right, and the other one with 20. And so with 10, you see that we have a certain set of bands, so the ribbon is not too wide, and the number of bands that we have is the number of sites that we have in the ribbon. But then if you take a wider ribbon, you get more and more bands. So the main difference is that as you make the system wider and wider and wider, then you effectively get more and more bands. And this is especially important once you put a magnetic field. So now let us put a magnetic field of, for example, 0.1 here and 0.1 there and see how the bands look like. And so the point is that when you put a magnetic field, you're going to have both bulk states and edge states. And of course, the edge states are going to be well decoupled between one edge and the other edge if and only if the ribbon is wide enough. So in this case, in which the ribbon is relatively narrow, the edge states of the top edge hybridize a little bit with the bottom edge, right? So this state over here, in a way, is not that far from this state over there. But once you make the ribbon wider and wider, then the two edge states are very well separated. And so you can see that the separation increases because in this case, we almost don't have any bulk states, right? Whereas here we have a very large set of bulk states. And then the last question is to replace a honeycomb lattice by a square lattice and see what happens. So what we are going to do now is we are going to use a square lattice. So for that, we are going to take square ribbon and see how the bond structure looks like. So you see that something similar happens, and it is actually easier to see if we actually increase the range in which we are plotting the energy. And so for that, what we can do is just to change this range over here. So let's put it from -5 to 5. And so you see that now we have actually a certain set of states that seem to be propagating towards the right, another set of states that seem to be propagating towards the left, and at the top of the band, the roll gets inverted. And you can actually see this more clearly if you increase the width of the ribbon. So the wider you make the ribbon, the more you are separating the edge states. And so the more clearly you see that you have bulk states, edge states propagating in the opposite direction. And so the appearance of bulk states and edge states when you apply a magnetic field is a generic feature that appears in any lattice, and it's called the quantum Hall state. And in a way, it is one of the simplest topological states. Okay, so now let us look at the localization of the edge states in the quantum Hall state. So for that, we are going to take a specific geometry, in particular an armature ribbon for the honeycomb lattice. We are going to add a magnetic field, and we are going to compute the local density of states at different energies. And so what we are going to see in this way is whether if the state is localized in the bulk or in the edge. and so forth. And so let us recompute this case. And as a reference, it can be useful to actually recompute the band structure of the honeycomb lattice. So we can actually do it in the previous. Okay, so let's take this one and let us compute the band structure exactly with the identical magnetic field. Okay, so at energy equal to 0, we have a bulk state. And so if you go to the band structure of the honeycomb lattice of the Aalto, you see that at 0 energy, you have this bulk state, and so that's why the density of states looks like this, all concentrated in the bulk. Then if you go to E 0.16, what you see is that you have states localized at the edges. And so if you go to this energy 0.16, you see that you are crossing effectively this state. Then for 32, you're also getting edge states. So 32 would be around here, so you still see edge states. And then once you go to 64, which is roughly around here, you see that you are cutting again a bulk state, and that's why you start seeing things in the bulk. And so now the first question is to recompute this with a smaller magnetic field. And so what we are going to do now is we are going to take just, let's say, 1/3 of the magnetic field, so 0.003, and see how the edge states and bulk states look like. And the most important thing is that, as you see now, the edge states are actually a bit more spread. They are a little bit more delocalized. And this is because the gap that appears in the quantum Hall state, particularly the topological gap, increases with the magnetic field. And eventually you see that you may be able to see this edge state, but the other energies, you just see bulk states. And so the next question is to recompute the previous local density states, but now with a narrower ribbon, and see what happens. And let us just remember this figure over here. So energy 0.16, we still have edge states, but they start to be not that far apart. And so we are going to take a ribbon that is a little narrower, and you see that now at 0.16, the edge states hybridize so much that they actually look like a bulk state. So in order to get these edge states, you need two things at the same time. You need to have a gap that is large enough that in this specific case is controlled by the magnetic field, and you also need the system to be wide enough so that the two edges are decoupled. Okay, now let us move on to the quantum anomalous Hall effect. So this is effectively a state that behaves very much like the quantum Hall effect that we discussed before, but now in the absence of an external magnetic field. So what happens in practice is that quantum anomalous Hall state, or the Chern insulating state, appears in systems that intrinsically break time reversal symmetry, not due to an external magnetic field, but due to the internal hoppings that the systems have, and in particular, in this case, due to an imaginary hopping in the honeycomb lattice that acts as a second neighbor imaginary hopping. And so what we are going to do is we are going to take this honeycomb lattice, so an armchair ribbon, we are get the Hamiltonian, we are going to add this topological gap. And the topological gap is called a Haldane coupling, and it's parameterized as a second neighbor imaginary hopping. And so the bigger you take this parameter, the bigger the gap you get. And so we are going to draw the ribbon, we are going to draw the band structure. And so if we recompute it, what you actually see is just the plot that it was shown before. And so now one of the important points to remember is that the phenomenology of the quantum anomalous Hall state is very similar to the quantum Hall effect. And this is what we are going to discuss now. So the first question is to make the ribbon narrower and see what happens to the edge states and why. So for this, let us just make another copy of this so that we can let's say see both images at the same time, and let's make it a little bit narrower. So instead of 20, we are going to make it 10. And so when you make it 10, you see that you still have the edge states, right? But now you can still try to make it even smaller. So let's say 5. So, and when you make it 5, you see that your edge states start hybridizing. In particular, they hybridize at energy equal to 0. And of course, this happens because the edge states are not that far anymore, And if they are not that far, you can have backscattering from one to the other, and this backscattering effectively creates this gap opening. Now, the next question is to replace the honeycomb ribbon by a zigzag ribbon and see what happens to the spectra. And so if you take, for example, this one, so we can replace armchair by zigzag over here. And you will see that we still have edge states. The band structure looks different, but the edge states still appear in the system. And this is what you effectively see here. So we still have a gap, and now the edge states are effectively appearing in different parts of the Bernoulli zone, but we have the same phenomenology as before. We have one edge state per edge, and of course, that coexists with a gap in the bulk. Okay, now let us move on to the edge states of the quantum anomalous Hall state. So what we are going to do now is we are going to take a certain geometry. We are going to get the Hamiltonian at our topological gap. That again, it is the Haldane coupling, and we are going to compute the local density of states at different energies of the electronic structure. So in this way, we will be able to see edge states and bulk states. Okay, so let us recompute this plot. Let us recompute this plot. So we are going to take, just as a starting point, a 6 different energies and a ribbon that has a width of 20. And we can try to compare these states with the actual electronic structure. So for that, we can go back to our previous example, use again our armchair ribbon, and compare with the electronic structure. And so while this loads, we can already notice something. So as we go from energy 0 to 16 to 32, we still see edge states, right? And this is something that you can also see in the band structure. So 0, 0.16, and 23, we are all the time inside the gap, and we are all the time crossing these states, and therefore that's what we see here. And then when you go to 48, 64, and 0.8, then you start going towards the bulk states. And so at these energies, you see that the states are localized in the bulk. And so we can now go to the first question. So at which energies do we have edge states and at which bulk states? So at this ones over here, we have edge states, and then at these ones over there, we start having bulk states. And then the next question is to increase the value of the Haldane coupling and see at which energies we now have edge states. And so what we can do is we can increase the value of the Haldane coupling over here, so 0.13. And you see that now with a bigger Haldane coupling, then we have edge states for a bigger energy window. And if instead we had decreased the value of the Haldane coupling, we would have gotten edge states in a narrower energy window, which is what you see with a smaller Haldane coupling. So with 0.06, you see that you start losing your edge states already at energy 0.32. Okay, so now let us move on to the next case, which is to look at zero-dimensional systems. So we are no longer going to focus on a infinite one-dimensional system, but rather on finite zero-dimensional systems. And for this, we are going to take a certain island of a honeycomb lattice that looks like this. So it's a hexagonal island, and we are going to see how the local density of states looks like at different energies for this island in the case of a Chern insulator. And so for that, we create our island. We create a certain Hamiltonian with a certain hopping. We put it at half filling, we add Haldane coupling, and then we look at the local density of states at different energies, and that is what it's plotted here. So for concreteness, we can recompute it again so that you see that we get the very same result. Now we can go through the question. So let us make the island smaller and see what happens to the edge states. And so for this question, the first thing that we need to notice is that as we go from energy 0 to 0.32, we see the existence of edge states, right? So this is very much as the previous case in the infinite ribbon. And then once we go to energy 0.48 and above, then we see that we have mostly bulk states. And so To make the island smaller, we can just decrease this number. So instead of 8, we can use 4. And if you use 4, you see that you start seeing things that look like bulk states earlier. And this is, of course, because your states between different edges starts hybridizing if your island is not big enough. If you go to big systems, then you see that you have very clear edge states up to the energies of the bulk gap, because your states in between different edges, they remain decoupled. And so this is the case that you see over here. So you see that you have very clear localized edge states up to energies 0.32, and then here you start seeing your bulk states. Okay, so now let us decrease the value of the Haldane coupling and see what happens to the edge state. So let us go back to case with n equal to 8, and let's recompute it to have as a reference. And so what we can do is to create another copy of this so that we can, let's say, compare one by one, and let us decrease the Haldane coupling. So instead of 0.1, let's take 0.05. And so in the case of 0.1, you see that you have relatively well-defined edge states up to, let's say, 0.32. But then if you take a smaller Haldane coupling, you see that the states are much more spread. So they are not so much localized at the edge. And in particular, 0.32, then you already see the bulk states. And so in practice, the Haldane coupling controls the topological gap, and the topological gap controls first, what is the localization length of your edge states, meaning that your edge states are more spread. And second, up to which energies you have edge states. So you are going to have edge states up to the energy of the gap. And then the next question is to change the number of edges in the islands and see what happens to the edge states. So instead of using an island of 5, we can use a relatively irregular island of, let's say, for example, 8 edges, and see what happens to the edge states. And so in an island of 8, the edges are no longer that regular, because we have, of course, a honeycomb lattice. But you see that we still have edge states, even though the island is not so regular, right? So the bottom line is that these edge states are protected, meaning that we don't have to have a perfect island or a perfect edge to have them, but they are going to appear in general for any generic edge. And this is something that you can see even more clearly by choosing a more irregular island, for example, with 5 edges. So you see that the edge states, they exist also in this island. They are, of course, oscillating a little bit because the edges are different, but they are robust and they will remain there regardless of whether you have impurities or rough edges. Okay, so now let us move on to understand these topological invariants. And so the topological invariants are effectively the object that determines whether if you have topological edge states, protected edge states, or you don't. And so for this, let us first take a honeycomb lattice at a certain sublattice imbalance that opens up a gap, and see how the simplest topological invariant that we can define, which is the Berry curvature, looks like in this system. So we can recompute this just for to see the result again. And so the whole idea is that the sublattice imbalance opens a gap, and this gap has a finite Berry curvature. So it has, let's say, positive Berry curvature in one valley and negative Berry curvature in another valley. And if you plot it in reciprocal space, it looks like this. But in total, this Berry curvature averages to 0. And so let us go through the exercise. So if you integrate the Berry curvature in the case of the Haldane coupling, would you obtain a non-zero value? So for this, we first need to add the Haldane coupling, right? So let us take, let's say, add Haldane, right? And we are going to add a 0.1. And you see that in the Haldane coupling, we actually have a Berry curvature that it's positive all the time. And this is what you see here. So you see that in the Haldane coupling, the bands look very similar, right? So you still have a gap opening at K and K prime, but now both valleys have a non-zero value. So you see that in valley K, you have a negative value of the Berry curvature, and in K prime, you have also negative value of the Berry curvature. So when you integrate this in reciprocal space, you will get a non-zero value, and in particular, you are going to get an integer, which is the Chern number. And this Chern number is the topological invariant of the honeycomb lattice, and it's the object that determines the existence of topological edge states. In contrast, if we had integrated the Berry curvature for the sublattice imbalance, then we would get a zero Chern number, and this is something that we can, let's say, see by recomputing the Berry curvature with some lattice imbalance as we did originally. And you see that in this case, you have here positive, here negative. And so when you integrate this over reciprocal space, this effectively cancels out the contribution from the other valley, and you get a net zero Chern number. And then the next question is to include simultaneously sublattice imbalance and Haldane coupling, and what happens when the gap closes. So for that, let us start with a large sublattice imbalance and with a, let's say, smaller, with a large Haldane coupling and smaller sublattice imbalance, so that we know that the Haldane coupling is winning. And so what you see is that in this case, you still have, let's say, a Berry curvature that has the same sign everywhere in the Brillouin zone. Now it's a little bit asymmetric between the two valleys. So one valley has bigger Berry curvature and the other one has a smaller, but it's still of the same sign all the time. So when we integrate this in reciprocal space, we are going to get Chern number 1. If you start slowly increasing the sublattice imbalance, so you can go now to 0.2, for example, you see that the gap in the band starts closing, right? So this gap over here starts closing, and the Berry curvature starts getting even more localized there. And eventually, if you take a very, very large, let's say, sublattice imbalance, large enough to overcome the topological gap opened by the Haldane coupling, then you will see that the one gets effectively a zero Chern number. So we can decrease a little bit of the Haldane coupling so that the sublattice imbalance can quickly overcome the Haldane coupling. And so you see that in this case, we are already in the limit in which the sublattice imbalance won. So we have opposite Berry curvatures in the two valleys. They are, let's say, not exactly the same in terms of absolute value, but then when we integrate this in reciprocal space, we will get zero. And so what happens in practice is that as you go from a topological regime that is dominated from the Haldane coupling to a trivial regime that is dominated by the sublattice imbalance, then the gap in the band structure will start closing. And once it closes, the total Chern number is going to change. Okay, so this is something that we can see more clearly in the next example. So we're going to look at the topological phase transition from this topological state to the trivial state. And so we are going to compute the topological invariant of the honeycomb lattice with both Haldane coupling and sublattice imbalance. And now we are going to do it exactly. So we are going to get the total Chern number with this function get Chern. So let us first recompute this. And so you see that for finite Haldane coupling but zero sublattice imbalance, then we get Chern number 2. Then if we start increasing the sublattice imbalance, we go to a limit in which the gap closes, and then after the gap closes, we get a Chern number 0. And so we can go through the first question. So you double the strength of the Haldane coupling, at which value of the sublattice imbalance do you have gap closing? So for this, we can just go to a bigger Haldane coupling, so 0.1. And you see that at 0.1, you have Chern number 2 here, Chern number 2 here, Chern number 2 here, and afterwards Chern number 0. And so the bigger the Haldane coupling, the bigger the topological gap, and therefore the bigger the sublattice imbalance that controls the trivial gap needs to be in order to overcome the topological gap. Okay, so now let us move on to the to see this topological phase transition not in the bulk of the system, but at the edge of the system. So what we are doing now is to replace the bulk geometry by a ribbon geometry and see how the edge states behave in this ribbon geometry. So as a reference, let us use this very same Haldane coupling here as the one that we used over there, right? So we are going to use 0.5, and let us use a relatively large K-mesh so that we get a very well converged, let's say, chair number. Yeah, or perhaps even bigger, and see how the edge states correspond to the churn number. Okay, so let us start with the case with zero mass. All right, so in the case with zero mass, we are in the topological phase. So we have one state here and another state there. And actually, this Hamiltonian has a spin degree of freedom. So here we have two states, and here we have another two states. Then you start increasing the sublattice imbalance. So you go to 0.17. So this gap starts closing over here, and this one opens. And here you still have two edge states, right? And this means that you have chair number two. Note that when your gap is very small, you need a very large K-mesh in reciprocal space to get the chair number accurately. So that's why we actually increase the K-mesh over here. And then if you keep increasing the sublattice imbalance, then you get a gap inversion, right? And now the gap opens up again, but now you don't have any in-gap edge states anymore. You have these states here, but these states are not topologically protected. And so in this regime, you have chair number equal to 0, which is what you observe over there. And if you keep increasing the sublattice imbalance, you still open the gap even more, and you have a trivial gap. And so let's go through the exercise. So at which value do the gapless edge states disappear? Well, they disappear roughly at some point between 0.17 and 0.33, right? So how does the value compare with the value for the bulk gap closing? And so the answer is that it is identical. The edge states disappear exactly at the same point as when the bulk gap closes. And then the next question is to compute how this very same phenomenology is for an armchair ribbon. And so for this, we can just replace the zigzag ribbon by an armchair ribbon, right? And you will see that in the armchair ribbon, the situation is identical. So the edge states are going to be located in a different part of the Brillouin zone. That's okay. That does not make a big difference. But in practice, you see that the edge states will disappear once we have the gap closing. So here you have presence of edge states, and now here the edge states disappear, and you see that after this point, then you have a trivial gap opening. So again, the gap closing happens at some point between 0.17 and 0.33. Okay, so now let us look at some finite size effects in topological systems. And so the whole idea is that we are now going to see how one can get hybridization between edge states when the width of the system is not too large. And this is very similar to what we discussed at the beginning of the session. And so we are going to take a honeycomb zigzag ribbon. We are going to create an artificial churn insulator. So we are no longer going to add a Haldane coupling, but we are going to add two different couplings that together they create a churn insulator. And these two couplings are a combination of magnetic order and spin orbit coupling. And so we are going to add our exchange coupling. So this is a magnetic order in the out of plane direction, and then Rashba spin orbit coupling. This is a spin orbit coupling that appears when you have broken mirror symmetry in a two-dimensional system. And we are going to compute the band structure, and we are going to do this for different widths of the ribbon. So let us recompute this just to see that we get what we were expecting. And then we go through the questions. And so, okay, so let's go through the first question. So why is there a gap in the edge states for narrow ribbons? And so the whole point is that if you are in a system that has a very large width, you will see your decoupled edge states, right? So you have two edge states actually on one side of the ribbon, two edge states on the other side of the ribbon, right? And these are topological edge states, and they arise due to a chair number 2 in the electronic structure. But then as you make the ribbon narrower and narrower, then these two states that in principle they are localized in opposite edges, they can start hybridizing because the edges are no longer that far apart. And that is what happens here. So when the width is small, so when the system is relatively narrow, then your two edge states hybridize and they open up a gap. Okay, so let us go to the next one. So make the rush spin orbit coupling 3 times as big. So what happens to the edge state? So for this, we take the rush band, we make it, let's say 0.3, for example, and see what happens to the edge states. And so the bottom line is that in this system, the topological gap is controlled by the combination of the exchange coupling and the rush spin orbit coupling. And in particular, if the exchange coupling is very big, then the gap opening is just proportional to the rush spin orbit coupling. And so you see that if you increase the rush spin orbit coupling, you are effectively increasing the topological gap, and this makes the edge states more localized at the edge. And so in practice, this allows you to have edge states that are decoupled even in relatively narrow systems, just because the gap of the system gets bigger. So the interplay here is that one needs to have a ribbon that it's wide enough so that the edge states are not coupled, and the coupling of edge states is given by their localization length, and the localization length is effectively determined by the size of the topological gap. Okay, now let us go through the third question. So what is the energy scale that determines how wide the ribbon should be to have a gapless edge state? So this is exactly what we mentioned before. You need to have a ribbon that it's wide enough so that the localization length of the edge states is substantially smaller than the width of the ribbon. And that is controlled by the by the size of the rush spin orbit coupling in this case. So for example, if you take a very low rush spin orbit coupling, your topological gap is going to be very small, and you may even have hybridization between edge states, even if your ribbon is relatively wide. So you see that even for a width of 20, you still have a little bit of hybridization between the edge states, because the edge states have a very large localization length. Okay, so let us now move on to the quantum spin Hall state. And so the quantum spin Hall state is effectively like two copies of a Chern insulator. You have a Chern insulator for spin up and the opposite Chern insulator for spin down. Together, they do not break time reversal symmetry because the spin up gets mapped to a spin down. So in practice, you can think that a quantum spin Hall insulator is like two, let's say, two Chern insulators that one is the time reversal of the other, one for one spin and the other one for another spin. Okay, so the way in which we are going to create a quantum spin Hall insulator is by adding intrinsic spin orbit coupling to the honeycomb lattice. So if you have a honeycomb lattice and you add intrinsic spin orbit coupling, then you get a quantum spin Hall insulator automatically. And we are going to add a little bit of disorder just to see what is the robustness of the edge states that appear. Okay, so and this is effectively what we see. So we are going to compute the band structure, and we are going to color the bands according to the location where they are in the ribbon and according to the sign of the spin projection. And so if you add this intrinsic spin orbit coupling to the honeycomb lattice, you get something like this. This marks the edge location. This match says the spin projection. And so you see that you have effectively two states per edge, right? So there are two red ones and two blue ones, and they have opposite spin projection. So now let us look at the question. So at which edge and what is the spin projection of each in-gap state? So for this, it can be actually convenient to add a little bit bigger disorder so that we see them a little bit more separate. So let us add something like this and see that when we add this bigger disorder, then the states are going to separate a little bit more, and we will be able to see them more clearly. Okay, so here they are. So you see that these two states, so the two red ones are localized at the bottom, and the blue ones are localized at the top. Now, if you look at the spin channels, you see that those two that were localized at the top, they have opposite spins, and those two that were localized at the bottom, they also have opposite spins. So what we have in the quantum spin Hall state is we have helical edge states. What this actually means is that at each edge, we have one spin channel propagating one direction and one spin channel propagating in the opposite direction. And that is what you directly see from this band structure. Okay, so now let us move on to the next one. So the system has disorder, and yet the states in the gap do not hybridize. So how can that be? So the whole idea is that the quantum spin Hall state is protected by time reversal symmetry. What this actually means in practice is that the crossings of these two bands, so the spin up and spin down, it is protected by time reversal. And in practice, as long as you add a perturbation that does not break time reversal symmetry, then this crossing is going to be robust. It is not going to change. And one way of seeing this is, for example, by adding another type of spin orbit coupling that mixes the spin channels. And this is Rashba spin orbit coupling. So let us add a little bit of Rashba and see that actually the edge states, they remain there. They are not destroyed by it. So what is important is that the intrinsic spin orbit coupling in the honeycomb lattice conserves the SC component of the spin, but once you're at Rashba spin orbit coupling, then the two components get mixed. But even when they get mixed, you actually still have edge states. And so that is what you see here. So you see that now the bands are fairly similar, but still you have gapless edge states, right? You see that the states are still crossing over there. You didn't get anti-crossings in these states. And this is maybe easier to see if you, let's say, lower a little bit the size of the disorder. So here what you have is a system in which spin is no longer a well-conserved quantum number because you have Rashba spin orbit coupling, you have disorder, and yet the states are crossing over there. And this is, again, protected by time reversal symmetry. Both Rashba spin orbit coupling and disorder do not break time reversal symmetry, and only when you break time reversal symmetry, then you can get a gap opening. And we can try to do this. So let us now break time reversal symmetry. And so one way of breaking time reversal symmetry is by adding an exchange field. So we can add a little bit of, let's say, magnetic field in the x direction. And you see that now that we add a magnetic field in the x direction, then there will be anti-crossings in the bands, and the states are no longer going to be protected, specifically because this exchange field breaks time reversal symmetry. So you see that now we have this gap opening over there that we didn't have before. Okay, good. So, and then the last question about the quantum spin Hall effect is to make the system narrower and see what happens to the in-gap modes and why. And so this question is very, very similar to what we observe in the case of Chern insulators and quantum Hall insulators. And so what we can do is we can make a copy of this just to see both of them at the same time. And so we are going to take a smaller width. So let's take, for example, 7. And you see that for a width of 7, the edge states are no longer going to be robust, or not that robust because the system is narrower. So, okay, maybe we need to make it smaller so that the anti-crossings are, let's say, more obvious. So let's make it 4. And so if you have it with 4, you see that now there's an anti-crossing over here. And this anti-crossing happens because the system is too narrow and the states that are localized in one edge actually hybridize with the states that are localized in the other. So you see that these two states, red and blue, they are localized in opposite edges, and then they have a little bit of hybridization over there. Okay, now let us move on to the next point, which is about the robustness of the quantum spin Hall state. And so the whole idea is that in the quantum spin Hall state, you can add two different types of disorder. You can add non-magnetic disorder, and you can add magnetic disorder. And this is effectively what we do here. So we are going to plot the band structure in 3 different cases. So first without disorder, then with non-magnetic disorder, and then with magnetic disorder. So the way in which we add non-magnetic disorder is the same as before. We add a on-site energy that it's random in each different site. The way we add magnetic disorder is by adding an exchange coupling that it's random in each different site. And then we see the band. So you see that without disorder, we get our protected gapless edge states. With non-magnetic disorder, we still get our gapless protected edge states, but then with magnetic disorder, then we have a gap opening. Okay, and so let's go through the question. So the first question is to take an armature ribbon and recompute the previous band structure and see if we get the same phenomenology. So for that, we can just replace zigzag by armature and see how the bands look like. And so the idea is that this phenomenology of no gap opening with non-magnetic disorder and gap opening with magnetic disorder happens regardless of which geometry you take. So without disorder, you see your gapless edge states. With non-magnetic disorder, you see your gapless edge states. And with magnetic disorder, you see that now a gap opens up. So this is universal, and this does not depend on how the edge is. It only depends on the fact that with non-magnetic disorder, you are not breaking time reversal symmetry, but with magnetic disorder, you are breaking time reversal symmetry. Okay, let's go to the next question. So take a supercell of the system and repeat the calculations above, and whether if you see the same phenomenology. So for that, we are going to take a supercell. And so what we are going to do is we are going to get supercell. We're going to make it twice as big. And so the whole idea is that when we add disorder to a ribbon, we are effectively adding the same disorder in every single unit cell. So we are, in a way, having a certain periodicity of this disorder. If you take a supercell, then you are adding a periodicity of disorder that it's bigger, so you are much closer to a realistic disorder in which no translational symmetry remains. What happens in practice is that this is not too important. So you see that even with a bigger unit cell, you still get that with no disorder and no magnetic disorder, gapless edge states arise, and with magnetic disorder, then you have a gap opening. Uh, and now, then we need to think about how this can be rationalized in terms of topological invariants. And so the whole idea is that in the quantum spin Hall state, the topological invariant is the set2 invariant. That's the invariant that you get from having a system with time reversal symmetry. And in particular, in the quantum spin Hall state, we have a non-trivial set2 invariant, which essentially means in practice that every time that we have a topological system with non-magnetic disorder, we are going to have protected topological edge states. Okay, so now let us move on to compute this topological invariant. So we are going to take a two-dimensional quantum spin Hall state and compute the topological invariant. So we are going to look at systems that have, let's say, different values of the sublattice imbalance, just to open a trivial gap. And we are going to plot, we are going to add, let's say, spin orbit coupling to the system to open the topological gap. We are going to add sublattice imbalance to open a trivial gap. We compute the bands, and then we are going to compute the set2 invariant, which is the topological invariant of the quantum spin Hall state. And we are also going to compute the band structure of the ribbon at the same time, just to follow how the topological invariant in the bulk evolves together with the edge states of a ribbon. So the edge states of a wide enough ribbon, in which we can see that there would be a correspondence between the topological invariant of the bulk and the edge. Okay, so let us go through this. So if we start with let's say, a small sublattice imbalance, meaning a small uh, parameter for the trivial gap, then we see that we are in the topological regime that corresponds to set2 equal to -1, and in this regime we get our gapless edge states in the ribbon. Now, if we start increasing the value of the sublattice imbalance, then we go through a topological phase transition, and this gap is now trivial, so we get a set2 invariant of 1. And in this regime, we no longer have gapless edge states, but we just have a gap, and we keep increasing the mass, then the gap becomes bigger. Okay, so let us count how many helical edge states we have in each edge for the one system for each case. So at 0 energy, here we have one pair of helical edge states, 0 helical edge states, 0 helical edge states. Okay, now let's add rush bus spin orbit coupling and see if we still have edge states. Okay, so for adding rush bus, we can just do it here. So let's say add rush bus. Here we added a little bit of Rush spin orbit coupling, and then the topological invariants are effectively the same here. Get topological invariant -1, which means topological. So we have our gapless edge states, and then here is 1, here is 1, and so we have our trivial gap. And then the next question is to add a second neighbor hopping and see if we still have the edge states. And so for that, we do it here. So we can add our second neighbor hopping over there. and see that in the presence of a second neighbor hopping, that breaks also some symmetries of the honeycomb lattice, which in particular is chiral symmetry, and creates electron hole asymmetry. We still have our H state. So in this case, you see that the spectra is no longer electron hole symmetric, right? So it seems that the splitting over here is a bit smaller than over there, and that's what second neighbor hopping drives. But even in this case, we get this correspondence between finite topological invariant or non-trivial topological invariant in the bulk and helical edge states. Okay, and now we are going to discuss a third type of topological state, which is the valley Hall effect. And so the idea is that the valley Hall effect is what is called a weak topological state of matter. What this actually means is that it is not as robust as other topological states of matter, meaning that there's no a fundamental symmetry that protects it, but it's an approximate symmetry. And this approximate symmetry is what is called valley symmetry. And so the whole idea is that if you have a system that has several Dirac equations, you could think that you can define independent topological invariants for each Dirac equation. And if you are in a situation in which the different Dirac equations are decoupled, then you can have topological states for each Dirac equation that is independently protected, as long as there's no scattering between the different Dirac equations. And this is, of course, an approximate protection because the Dirac equation is a low energy approximation. And if you have very strong perturbations, then you can always break this low energy approximation. But this is very, very important because it appears, for example, in multi-layer graphene systems, and it can be controlled by an interlayer bias. So let us do this example. So what we are going to do is we are going to take a bilayer graphene, so just two layers of a honeycomb lattice. And what we are going to do is we are going to add a bias between them. What this means in practice is that we are going to add a different on-site energy in the bottom honeycomb lattice and in the top honeycomb lattice. And so that is what you see here. So the plot on the left is the band structure without a bias. So without a bias, this bilayer honeycomb lattice is gapless and it has this quadratic crossing over here. And then when you add a bias, you effectively open up a gap, and this gap has a finite Berry curvature. So you see that if you go from one valley to the other valley, then the Berry curvature changes. And if you integrate the Berry curvature in the whole space, you would get 0. But each valley independently has its own Berry curvature, and it integrates to 1. And this is actually more interesting if you look at it in a ribbon. So if instead of considering a two-dimensional infinite system, you take a ribbon made of this bilayer honeycomb lattice, you see that you are going to get edge states that appear because of these independent Chern numbers. So this is what you observe here. So this is the band structure of a bilayer ribbon. And you see that there's this edge state over here, this edge state over there, edge state over here, edge state over there. And this crossing here is protected by, this crossing over here is protected because they are located in different edges. And then these states over here belong to one valley, meaning one Dirac equation, and these states over there belong to the other valley, meaning the other Dirac equation. Okay, so let us go through the question. So discuss what is the direction of the propagation, valley quantum number, and location of each state. And so the direction of propagation, this is towards the left, towards the right, towards the left, towards the right. And so if we focus on the states that are located in one edge, what we get is one state that propagates towards the left, another one towards the right, and that they have different valley number. So what we get here is actually valley helical states. So in one edge, we have two states. One propagates towards the right and belongs to one valley, and the other one propagates towards the left and belongs to the other valley. So as long as valley is a good quantum number, as long as we don't have scattering between different Dirac equations, then these two states are not going to hybridize.